Okay, so here's a rational function that we're going to determine the points of inflection in cavity for. So you're going to have to take the second derivative. If you're a little rusty on derivatives, I would suggest you go ahead and do that. Pause this video and do it if you think you're good or lazy. Here's what Wolfram Alpha told me. So I'm typed in find the second derivative. Now, if you're going to use Wolfram Alpha on these, look what they give you. They give you this mess. That's not going to be very helpful. But if you scroll down and look for alternate forms, look for the best one. This looks like the best factor one. That's what I'm going to go with. So my second derivative, I'm writing this down as I say it, is 10x times the quantity x squared plus 12 over the quantity x squared minus 4 to the third. So I went ahead and wrote that down. Here it is. And now I'm ready to do all of my work. So we have to figure out where the second derivative is 0 or undefined. So the second derivative equals 0 when you factor, well, these are factored. So obviously when x equals 0. And then when x squared plus 12 equals 0. But x squared plus 12 does not equal 0. It can't, because this is a positive plus another positive. If that doesn't make sense, just try it. If you try to set x squared plus 12 equal to 0 and solve, you will get x squared equals negative 12 and x equals this plus or minus the square root of negative 12, which is not a real answer, so it's not on the graph. So y double prime equals 0 at x equals 0, and it's undefined at x equals plus or minus 2. Be careful there, those could be asymptotes. So these are your possible points of inflection. Now, if you think about it now, you can eliminate plus or minus 2. They can't be points of inflection if they're asymptotes, and they are. But you could consider them possible right now and eliminate them later. So possible points of inflection is not that strict on your definition. So you may include the asymptotes, or you don't have to. But x equals 0 must definitely be a possible point of inflection. Now, when you draw your chart, make sure that you include the asymptotes, plus or minus 2, but include them as dashed lines so you'll know you're not going to call them points of inflection, because you can't have a point of inflection where there's no point. And there can't be points at asymptotes. But you need to include them because anything can change. So you can change concavity at asymptotes. So here we go. Check the second derivative at negative 10 here, the second derivative at negative 1 here, the second derivative at 1 here, and the second derivative at 10 here. If you plug it into the second derivative, remember, this part's always positive, so that's going to be easy. If you plug in a negative 10, you get a negative times a positive over, that's going to be positive cubed, so positive. So you have a negative divided by a positive, which is negative, which means concave down on negative infinity to negative 2. When you plug in negative 1, you're going to have a negative times a positive. Now, negative 1 squared minus 4 is negative. Negative cubed is negative. So that's all over a negative, which is a negative over a negative, which is positive. So I can say we're concave up on negative 2 to 0. I'm going to plug in 1 now. Get a positive times a positive over negative cubed, which is negative. So we're concave down on 0 to 2. And finally, you plug in 10, everything's positive here. So it's concave up on 2 to infinity. So that's the discussion of concavity. I've determined the concavity of this graph. And now I need to figure out what the points of inflection are. Points of inflection are the points on the graph where the concavity changes. Concavity changed a lot, but the only point it changed at was 0. So point of inflection is at 0, comma. Now whatever the value of the function is when you plug in 0. So you don't see it now. You have to look at the original graph right here. When you plug in 0, you'll get 0 over -4, which is 0. You can check on your graphing calculator. I have already typed it on Desmos, I believe. I'll find it now. Hold on. So you can see I typed it on Desmos. It goes concave down to concave up. Point of inflection here, because then it changes the concave down. And then over here it's concave up. You can see the two asymptotes. That looks perfect.